This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. All right, guys, welcome. So exciting, we got our course books in. So we have enough for everybody. So if you guys want to go ahead and come up and grab a book, and then there's also pencils for you. All right, so go ahead and take a minute and just look through it, page through it. So the reason you guys were given a pencil, and I think we talked about this last week, but the reason you guys are given a pencil is the intent is for you guys to write in this, right? So do not feel bad when you go through practice problems. Right, you'll notice that there's a whole page dedicated to a practice problem. That's not because I hate paper and trees. That's because the idea is for you to use the area below on which to write. Okay? So go ahead and take just a couple seconds to look that through. Let me know if you have any questions. Otherwise, we will get started with unit number 2, which is units and conversions. So who here is bored out of their mind doing units and conversions? It's fine if you are, right? But why is it important? It's not important at all? All right, fair enough. All right, well, let me make my case. All right, so first I want to talk about engineering skills, right? At the beginning of every lecture, what we do is we're going to do like a 10 to 15 minute thing on a topic of engineering, like chemical engineering or something like that, just to let you know what it is. For today, I want to talk about engineering skills. So what do I mean, Emma, by engineering skills, do you think? That's pretty much nailing it on the head. I love that answer, right? So engineering skills are what it takes to be an engineer, or skills that people who are successful engineers possess, right? Because there's plenty of people out there who have engineering degrees who maybe aren't the greatest in the engineering field. All right, so what it really boils down to for me and for you, because what's the whole purpose of you guys going and getting a degree and going through all this work at school is ultimately to get a job, right? I would hope. Okay? What you really want to be thinking about as you're going through your education even now is, what is the person who's going to hire me one day? What is that person looking for, right? And then you can tailor your internships and your other activities accordingly, right? They want more than just a degree, right? There's going to be a lot of people coming out with a degree. The question is, why do they want to hire Connor, right? Why should I hire you tomorrow, Connor?
Because gain the skills
through education,
yeah.
And you're a hard worker, right? That's everybody's answer, right? So what's going to set Kate number 1, actually you're William, so you're actually Kate number 2. So what's going to set Kate number 2 apart, right? What's going to set you apart? Okay, that's what I want you guys thinking about. So fundamentally, the skills that an employer cares about is all these here with my little dude giving a thumbs up, right? He's a happy guy, he got employed, that's why he's got a laptop, all right? So what we're looking for is engineering knowledge, professionalism. Did I come here in board shorts and a Metallica t-shirt to teach you guys? No, I came here a little more formal, and why is that? What do you think that is, Jordan?
Because teachers should be wearing formal clothes.
Why?
They're going to their job.
Okay, that's fair. But would you take me seriously if I was in here and like had my dirty shirt on from last week? Would you take me as seriously as my level of success, right? Yeah, you don't want me to look like the guy begging for change on the street corner, right? You want me to look like someone who actually knows what he's talking about in terms of getting you guys hired, right? Also, you have to be a team player. You guys are probably sick and tired at this point in your life already of doing team projects. You probably have 2 to 3 team projects a semester, maybe even 1 in every class, right? But why are your teachers continually putting you through that? So that you can learn how to work with other people. And unfortunately, it's so you can learn how to work with difficult people. That is actually a skill that you need to pick up, right? Aside from general knowledge, communication, this is one that we as engineers take flack on a lot, is our ability to communicate, right? People are like, oh, engineers are weird, they can't communicate. it's not actually true anymore, right? If I fail to communicate to people in my job, it's no different than failing to communicate to someone on a daily basis, right? We can't get things done. When you're working as a team, you can't succeed if you can't communicate with each other. Another big one is customer focus. This is one that really has come up probably within the last 20 years, especially when it comes to computers. And the main driver in this was Apple, in my opinion, was Apple. It used to be that if you had a PC and you had Windows, there was a way that the computer worked, and that was the way the computer worked, and you learned how to use it. What Apple really did is they came on and they kind of functionalized the computer the computer to be more intuitive and work the way to be more user-friendly instead of just designing it how an engineer thinks it should work. They designed it how the people who were they designed it for the end user. And we start to see stuff like this a lot, even when it boils down to like parking lots, right? So there's a safety concern when, like, if you park your car at the mall and you need to go to the mall and you're weaving in between cars, there's a problem with that because other cars coming down the other line might not be able to see you when you pop out, right? So what they want people to do is they want people to walk down the aisles. But one thing that people, engineers, the civil engineers who design the parking lots will fail at a lot is they won't let those walk paths go towards the door, right? So when Kate gets out of her car and she wants to go to the mall, she's super excited to get to the Gap or Forever 21 or whatever, right? She's going to take a straight line towards the door. And we as engineers should design the paths to do that because that's naturally what a human wants to do. So instead of thinking this makes more sense because I can cram more cars in if I do it this direction, instead you need to be thinking about how is the user going to use this, right? The traffic engineers all the time, we see this, we're like, wow, this is a 3-lane highway, but this merge is still a bottleneck. Why is this a bottleneck? It's because it was designed perfectly from a theoretical point of view, assuming that no human was an idiot and didn't know how to merge, right? The problem is no one important knows how to merge, and then what happens? We have traffic jams everywhere, right? So instead of designing to the textbook and designing the way that you think it needs to be done, you need to get in touch with your customer and understand what their needs are and make sure that it's designed for them. It doesn't matter whether or not it's intuitive to you, it has to be intuitive for them because ultimately, if it doesn't work, no one's going to buy your product, right? Okay. Another one is safety conscious. This one goes without saying. I know that this is pounded into you guys every day that you go to class. Safety first, don't cut off your thumb, don't burn yourself with a Bunsen burner, whatever it may be. But the fact is, it really costs companies a lot of money when people are damaged, and it ruins people's quality of life. You don't want anybody going home without a finger or without an arm because of something that was prevented, right? So that's something that we have to think about in every procedure we write and every design that we make. The next, of course, is quality-oriented. What do I mean by being quality-oriented at DT?
It should, the product or whatever you're engineering should be able to suit the customer's needs.
Correct, and for a long time, right? Or at least for the duration specified, right? And we will actually talk about that in our reliability engineering class. So these are, I only touched on a couple of these, but these are all very big things that they're skills that employers are going to be looking for, things that you should be focusing on not only in your job, but in developing your own skills. Okay, so what makes a good engineer? We're not going to go through all these because I don't want to be here for an hour, right? But obviously you guys know about problem solving. I think we pounded that into the ground last time. I hope I got that across. So you will also be required to demonstrate technical competence. This one speaks for itself. You're going to have to go through a grueling 4 or 5 year education, depending on your plan. You're going to have to pass tests, and you're going to have to show that you know how to do math, you know how to do physics, and you can do it. That you're going to solve on your own. The next one, and this is one that you guys are going to have to learn, you're probably actively learning right now, but you're going to have to even more deal with it in engineering school, is time management, right? How do you manage having a job to pay for school and getting to your classes? How are you going to decide, I only have 10 hours to put into homework this week, this project's going to require 15 hours, which class am I going to take the B in, which class am I going to take the A in, right? Those are real life decisions that you're going to have to make that will apply to your job, okay? Attention to detail. The slightest miscalculation can cause an entire product to fail. One of the items we're going to talk about tonight was a satellite that crashed onto Mars because somebody missed a small detail in their planning. Okay, communication skills, we talked about that. Now, people skills, this one is different than communication skills. What do I mean by people skills, Andrew?
Just being able to get along with people, I guess.
Mm-hmm. Is it always about getting along with them, though? All right, let me rephrase the question. Do you have to like them?
Not necessarily.
Right. but you have to work together, right? Yeah. So the big one here is what you're going to have to learn, and I kind of talked about this already a little bit with how you're going to have to interact with your customer and kind of teach for your customer, right? You may leave the room thinking this customer is the biggest idiot I've ever met in my life, but it doesn't matter because you still need to deliver them a product and they're still the one paying for it, right? So you're going to have, for example, if Jeremy, if you're telling me your boss about your project, you're going to probably talk to me in a very different way than you might talk to the customer. You might have to dumb it down for the customer, and you might have to dumb it down for me versus your colleague on the product, right, that you're working with on the project, right? So you're going to have to be very adaptable on how you communicate with different people. Next is teamwork. This goes without saying. This kind of goes back to what Andrew was talking about as well. You don't necessarily have to like someone, but you're going to have to be an effective team player. And furthermore, you're going to have to learn leadership skills. And one of the hardest leadership skills to learn is that you don't always have to be in charge to be the leader, right? You don't have to be the boss to be a leader. You can lead from within. And sometimes those are the most effective leaders. Next is a flexibility and willingness to adapt. Especially in industry, goals change all the time. We talked last week about, we theoretically talked about a project that you're on and you're almost done and your boss comes to you last minute and says the scope just changed and now you're working over the weekend, right? Stuff like that happens. You can't get too committed to your end goal. You have to get committed to your end goal of finishing the project, but you can't get too attached to any one specific thing because you may have to change, right? Maybe you were a little delayed, somebody else beat you to market, and now you have to improve the next rev so that you can beat them to market on the next rev, right? That's just the way it works. And this one we talked about already, leadership skills, right? Leadership is about action, about taking action, and about leading others in the way. That doesn't mean you have to be in charge to do it. Okay? So becoming an engineer, what do you need to do first? You need to get a degree, right? How are we going to do that? We're going to take this class and then we're going to go to school. We're going to get straight A's the whole time. It's going to be super awesome, right? Probably not A's the whole time, but that's okay. Right, so at most institutions, an engineering degree is going to take 4 years. There are some programs out there that will take 5, but usually what those do is they put you in some sort of co-op program the second semester of your junior year, and then the first semester of what would have been your senior year. So you essentially take a year off, but it gets you real world experience. Usually those are with 2 companies. I've heard of it being with just one company before, but usually the idea is that they put you in multiple industry positions and kind of get you a better idea of what's going on out there. Generally, the first 2 years are what we call foundational. So Ryan, you're going to major in electrical engineering, and Connor, you're going to major in aerospace. I don't know if that's true or not. I don't remember. But you guys, even though when you guys are seniors, are never going to see each other because you're going to be in the aerospace lab and you're going to be in a dark room putting circuits together, right? You guys are never going to see each other when you're seniors, but the first 2 years, you guys are going to be best buds sitting next to each other in the same classes because what we're learning is the fundamental stuff like physics, chemistry, and stuff like that, right? Even some of your introductory engineering courses you may take together. But after that, you're going to start branching off, okay? So why do we, as engineers, care about those first 2 years? Why do we in this class care about those first 2 years? Because that's what we can get a leg up on. If you are not focused as much on seeing stuff for the first time and you have experience on it, it's going to be easier for you to pick it up. It's going to put you farther ahead, and it's going to let you put more calories, more of your percentage of energy that you have into the places that you need to focus in school to be successful. Okay? So I'm actually going to shut off the lights, so I apologize, or just be aware for your eyes. All right, so this is a sample curriculum of actually from Tulane where I went. But this is a sample curriculum of a first year engineering curriculum for chemical engineering. So what you'll notice is that you're taking general chemistry, general chem lab, general physics, calc 1. This engineering tides is basically a intro to engineering type course. And then you're taking an elective for writing. Is there anything in there that screams chemical engineer? The answer is no. Right? Maybe chemistry because people associate that, but even if you're an electrical engineer, you're going to be taking chemistry. Okay? Then we see it's pretty much the same second semester. So first year, there's nothing in this entire first year that will set you apart into any one engineering discipline. The next year now, we start to get maybe a little more specified. But again, look, we're looking at, so we have material and energy balances and thermodynamics. And then we have intro to biotech and biomolecular and transport. So those are very certainly chemical engineering track focused, right? You're not going to have a computer engineer taking those, but you are going to have environmental engineers taking those, and maybe even civil engineers taking those, right? So you're still going to be with some breadth of other engineering students. Then of course we have organic chemistry. You're going to be in organic chemistry with a lot of doctors. Good luck on that class. That's an awful, awful, awful class, because it is the doctor, so all doctors have to take that. It's like one of the things that med schools look at is how well they did on organic chemistry. So they will load their schedules up to take like basket weaving 101 and 102 the same year that they take that, so they don't have a lot of credits. Meanwhile, you're taking a bunch of engineering classes and getting your butt kicked. So you have to put effort there just to stay alive. And then you're taking Calc 3, Introduction to Applied Math, which is just Diff-EQ basically. And then you're taking Cultural Knowledge, which are just electives. But now in this third year, look at this. We have thermodynamics, numerical methods for chemical engineers, transport, an elective, and then a technical elective. There's nothing on there that is general engineering anymore. In this third year, we're completely 100% into what we're studying. And then the fourth year of engineering is really interesting because we have these process design classes and then practice school. And you notice practice school is actually 6 credits. When I was in practice school, I actually didn't go to class. It was just really time dedicated to us working on a real world project. We were paired up with a company, we were paired up with a consulting company, we had a project we were working on them with and spent a lot of time with them, but we didn't actually go to class with it, right? At this point, you're basically an independent person just trying to finish your studies. Then of course, you have to finish your electives. You have an advanced chem elective really. But at this point, you're pretty much by your senior year, your main focus is going to be completing your, they call it a capstone project. Then there's, oh, sorry, let me turn the lights back on now. Watch your eyes, watch your eyes. All right, so do I have anybody in here who's thinking about getting a master's or a PhD? Nobody? You're all smart. I like it. All right, so postgraduate studies, if you decide you want to go teach or you want to do research, that's maybe something that you're thinking about. So a master's can give you the extra edge when applying in industry for jobs. We typically see, I mean, everybody is different personally, but we typically see that when the economy is good, we have less master students, right? The reason is you can get a better job right out of being a bachelor, being with their bachelor's degree, I mean. So why would you pay for the extra schooling? All in times when it's harder to get a job, you'll see people go ahead and get that 5th year just to give them a competitive advantage on the entry market, right? It makes sense. Then there's the PhD. The PhD program, the point there is to allow people to get experience doing research. One should not pursue a doctorate merely for the plan. So again, I have one, obviously I went through it. You should, if your plan is just to go work in industry in a normal engineering job, it's really poor value for both your time and your money to go get a PhD, right? What you should go get a PhD for is if you want to go work in a lab and start to do research to fight cancer or something like that. Or if you want to do what I do, which is research-based technology development, right? Something like that. If you want to just go be a normal engineer, I don't know what that means really, but if you just want to go be an engineer that you could do with a bachelor's or a master's, there's no point really in, because let's think about it this way, right? You're going to spend 4 to 5 years of your life getting a PhD. And you're going to start, let's say you get a great one and you start 30 grand higher, right? Think about the area under the curve. You spent, because what did we see? Remind me what we saw last time. It was like $65,000 a year was the average starting salary-ish, right? So let's say you go from 65, you spent 4 to 5 years in school not making $65,000 a year. Meanwhile, you're getting raises. Maybe you get a promotion and you're even farther above. It's even conceivable that at the end of 5 years of being in industry, you could already be making as much as you would have in an entry position to PhD, and you wouldn't have wasted that time under the curve, so to speak. You'd have all that money that you made during that time. Does that make sense? Am I being clear on what I'm saying? Right, so unless I'm not discouraging you from PhD, again, that's what I have, and I'm fine with it, like I'm fine with the decisions I made, but if it's not going to get you anywhere, that's what I'm just saying. If it's not going to get you anywhere, if you don't need it for what you want to do, then you should really take the time to think about if it's something that you want to do. Okay? Also do note though, just for disclaimer, PhDs in engineering, you generally don't have to pay for. So I did not have to pay for the degree, and I actually had a TA-ship, so I was making about $20,000 a year when I was in school. It's not very much. That's like top ramen and macaroni and cheese type income, but you're not paying for school, which is a huge win. Master's degrees, most of the time you do have to pay for, but they're only 1 to 1.5, maybe 2 years, so they're a lot shorter time period. All right, so any questions on that, just about the next steps? So that was just a quick primer on what you guys are looking for. Did anybody find the curriculum interesting? Have you guys been looking at school curriculums already? Okay, so we will talk about selecting an engineering school later. So in the meantime, I want to talk units and conversions, which is today's topic. Or not in the meantime. For today, I want to talk about units and conversions. So what do I have going on here? What is this? It's a ruler. What's on the bottom side of that ruler? Notches? 1, 2, 3. What's on the top side? 1, 2, 3, 4, bigger 5. Yeah, so we have inches on the bottom and we have centimeters on the top. Which one of those is right? Centimeters? That's a conditioned response. The answer is they're both right. They're both the same, right? If I measure a battery in inches and I measure a battery in centimeters, like the length of a battery, am I going to get a different result? Yes, no, interesting. The battery is the same size, right? Do we all agree about that? But it would measure, let's say, 5 centimeters and it might measure 1.5 inches, right? That's actually not the correct conversion, but you understand what I'm saying, right? Which one of those is right? They're both right. Yeah. What's that?
Just in different units.
Correct. Excellent. So now, why do we use units? Vikram, you're on the spot. Why do we use units at all? Can you go 2? Can you go 2? Can you walk to the back of the room and go 2?
Not unless I know the unit.
Not number 2, by the way. Can you walk to the back of the room and go 2? Or 5 or 4? No, you can't. I have to specify it, right? Go 2 and then take a right and go 3. You're not going to get to where I need you to go in my head, right? That's why we use units, right? So we have basic dimensions. Units are used to specify our dimensions. We have basic dimensions, which is something that can be directly measured. That's in the case of our ruler, right? How tall is Jeremy? We can put it in terms of inches, meters, centimeters, whatever we want, okay? Time we can measure. Mass we can measure. Temperature we can measure. And then we have calculated dimensions, which is stuff like we deal with in physics, right? Velocity is a calculated dimension, right? We can measure how far, and we can measure how long. Those are basic dimensions. But when we put those together to get a velocity, that's a calculated dimension, right? Simple enough. Okay? So, and then of course we have volume, which we see all the time. And then we also can have dimensions that are calculated using other calculated dimensions, right? The best example there is density, which is mass over volume, right? In order to get volume, we have to take how many lengths? 3, right? Because it's length to the third. All right. So any known quantity in the known universe can be expressed in such a fashion. In fact, we have to. So adding and subtracting. Units can be treated like variables, and they have to be treated like variables. So that first one up there, I have 2 meters minus 8 seconds. What's the answer? Come on, it's on your test. You have 1 more second or you fail. Yeah, you can't answer it, right? But the numerical values of any 2 quantities can be added or subtracted only if the units match, right? So I can't subtract seconds from meters. Obviously, you guys all know that. But 2 meters minus 1 meter is how many meters? All right, what is 2 inches minus 1 centimeter? So you can do it, but only after you do what to one of those units? Convert it. All right, slam dunk. Perfect. All right, we can also, and this is where our calculated dimensions come in, we can also multiply and divide. And in this case, it doesn't matter. We can do whatever we want with multiplying and dividing, right? It may not make physical sense afterwards, but we can do whatever we want with it. So we can say 2 meters divided by 8 seconds, there's your velocity. And likewise, we can do multiplication of non-like units. 5 meters times 3 kilogram equals 15 kilogram meters. I don't know what that means necessarily, but hey, it's a unit that we just calculated and it's completely valid. Then we can divide them, right? So there I have 10 grams per hour times 2 hours to get 20 grams, right? That's just backing out a flow rate. Or we have 3 meters times 4 meters per hour equals 12 meters squared per hour. Again, I don't know exactly what that means, but it still works, right? And there's a reason I'm using ridiculous ones that don't work. I'm trying to point out that we can do whatever we want, right? All right, so if you please go to your handbook on page 5. all the way up at the front. There is a table of contents though, so it's not quite at the front. What we have here is a sample problem. So A, I'm asking you to solve all of these. A is 3 meters minus 2 meters. B is 100 kilometers divided by 2 hours. And then C is 9 inches minus 2 grams. So I'll give you 30 seconds to run through this, and I'm going to start picking on people. All right, River, what do you have for A? 1 meter, does everybody agree? That was a pretty hard one. All right, fair enough. All right, how about B? Eva, what'd you get for B? You didn't get anything for B? What do we get for B? Kate Williams?
50 kilograms per hour.
50 kilograms per hour, correct. And then C, 9 inches minus 6 grams. Rana, what'd you get for that one? You didn't do it yet? Does anybody have C? You can't do it. That is correct. You cannot subtract grams from inches because they don't work together and it doesn't make sense. All right, so very well done. I think you guys got the point. That was a silly and stupid one, but I wanted to make the point. All right, so what is a ratio? Actually, I'm going to back up so you don't have it written in front of you. What is a ratio? Tom, what's a ratio? It's a fraction. That's technically correct. So what does a ratio mean, though? What's it telling us? There you go. Proportions of one thing to another, right? So ratio is really just a relationship between two numbers. So the one we talked about earlier was velocity, right? I'm saying I'm going 100 miles per hour. What that's saying is what? It's saying for every hour I drive, or every fraction of an hour I drive, I'm going 100 miles, right? Simple enough. So in this case, we have, if I have 9 people for 3 cars, I have 9 people per car. And in some cases, and these ones are actually very useful for us in engineering because dimensionless means we don't have to do what? Worry about units, right? So if I have 10 meters for every 5 meters, that would equal 2, and there would be no meters on that. Where would we see something like this? Where would we see a 10 meters per 2 meters? On a map? That's very good. The scale on a map. I hadn't thought about that one. That's very good. Okay, where we see this in engineering a lot is like in structural engineering when you're talking about rise over run, right? What is how high do my stairs go? What's the pitch of what's the maximum pitch of a ramp for a wheelchair, right? It can only go up 3 inches per every foot or something like that, right? That's very typical, right? Because you don't want your wheelchair to have to go up something like this. You want to have to go something like this. So there's codes for that, right? Okay. All right, rates. So a rate is a special ratio in which measurements of different units are related to each other. So for example, the one I already used was velocity, right? Is velocity a rate? Yes, no? Maybe so? Yes, we think it's a rate? It is, right? Velocity is a rate. Now in engineering, and this is one you guys are going to have to try to remember because it's what we're going to use during this class. In engineering, we use a dot over top of a variable to denote it being a rate. Some books will use it as italics, right? Instead of saying mass, they'll do italic mass for mass flow rate, or instead of, I don't know, anything, right? They'll use an italics. The reason we don't use italics in here is because what do we still do as engineers sometimes? We write things down, write them on a board. It becomes very different, or very difficult to distinguish between a handwritten M and a handwritten italicized M. So the function that we do, not only in this class, but most engineers, they'll put a dot over top of mass for a mass flow rate, right? And what do I mean by a mass flow rate, Andrew?
The amount of mass flowing over a certain time.
Correct, right? If I have that sink on, we might say, all right, I have 1 gallon per minute coming out of there. But what does 1 gallon of water weigh? I don't expect you to know off the top of your head, but the idea is that volumetric flow rate, in that case, gallons per time, can also be mass per time. And what do I have to do to get from my volume to my mass? You know it, you can say it. What's that? Well, you have to then use the density, right? Convert with the density, right? All right, so we do make exceptions though. There's a couple exceptions for variables that by definition are rates. For example, velocity. It's okay to just use V for velocity because that's what you've been doing for the last 3 years of your life with physics anyway, right? V is velocity, A is acceleration. It's okay, you don't have to put rates over that. Everyone gets that part, okay? But Oh, and amps is another one, right, when we're doing circuits. Amps is actually technically a rate, but it's also just a basic unit, so you don't have to use it for that. Okay? But the ones that we'll see, especially early, is mass flow rate, volumetric flow rate, and heat flux. All right, so here's the battery example I used, right? So unit conversion, I think you guys all understand this. In order to get from one unit to the other, we have to multiply by a conversion factor. Does anybody know what the conversion factor from inches to centimeters is? Off the top of your head? 2.54, very good. 2.54, very good. Very, very good. And I don't have this stuff memorized just because I'm a super nerd. You get it, well, I mean, I am. But you will get this stuff pounded into your head, right? About the 15th time that you go look up in a table what the conversion rate for something is, you're just going to remember it, right? It's like I bet half of you guys who have taken chemistry know what the molecular weights of carbon, oxygen, and stuff are because you've done it 15 times, right? Or 15,000 times, whatever. Okay, same idea. So in this case, these are just a group of news articles. But metric mishap caused loss of NASA orbiters. Anybody heard about this? This is a kind of a famous one. Yeah, a couple of you guys out there. All right, so fundamentally what happened was NASA shot a satellite off to go visit Mars. The problem was, and it was all perfectly designed, they got it up there, they got it to Mars. When they went through the landing sequence, they're like, all right, go land. And the satellite turned and took a face plant right into the surface of Mars. What the heck happened? Well, what the heck happened was one team who was developing one part of the program used metric, and one team who was developing another part of the program, or an execution software or something like that, did not use metric. So when you went to that conversion and it decided to take a slight cascading entry point, it was not so slight, right? So instead of going in like this, it said, and $1 billion out the door. Right? So do you think somebody probably got a stern talking to about that one? Yeah, that falls in the glad it's not me category, right? But this is kind of a classic example, and we kind of use it and we kind of laugh about it, but stuff like this does happen all of the time, right? You see it happen a lot of times at stores where something will be way mispriced because maybe somebody didn't quite do a conversion correctly from currency or something like that, right? It does happen, okay? So unit conversion. So I'm going to teach you the way that I was taught to do unit conversions. And it's going to, I openly admit that it's going to seem very silly at first because most of the conversions that you guys are doing often are very simple, right? For example, I need to go from inches to centimeters, right? That one's very common. That one's very easy to do because you just know it in your head, you can multiply. But the method I'm going to teach you is something that you're going to be using later on in your engineering career when you need to do multiple conversions all at the same time within one problem. So instead of having a separate sheet of paper to the side where you do a conversion, plug it in, do a conversion, plug it in, do a conversion, plug it in, I'm actually going to teach you a method that I use, or that, not, well, I use it, but it's a method that engineers use to keep it all in one place. So again, when you see this and you're wondering why I'm talking to you about this, don't brush me off immediately because it's silly. Just stick with me and I promise in a couple minutes it'll make sense, all right? So what we're going to do in this example is we're going to convert 500 grams to kilograms, right? So how many grams are in a kilogram, just off the top of your head? 1,000. Why is it 1,000? Because kilo's 1,000. Fair enough, right? So in order to do that, we use a conversion factor. There is 1 kilogram per 1,000 grams, or vice versa. But why do we put this on the denominator? So the units cancel. Very good, right? So I have a gram. This is really 500 grams over 1, right? That's the way that this is really working. So 500 grams over 1 times grams over kilogram. Whenever you have something in the numerator and something in the denominator, what happens? They cancel, right? So those grams kill each other. And what we're left is with 0.5, how much? Kilograms, right? Because I have gram over gram times kilogram, which leaves me with kilogram. Okay? So to do large conversions, we use a grid. Vertical lines in place of the multiplication symbol. So for the above case, we're going to make a grid that looks like this. 500 box kilogram 1,000. Okay? So again, this looks really silly when we can just do this, which is the nomenclature we're used to. But when this starts getting bigger and we're doing more, it's going to start to become easier. So does this make sense to everyone, that we're just going to make this grid? All right. So let's go to page 6 in your handbook, please. Should be right on the other side of the page if I did it correctly. And let's please convert 1 day into seconds. So does anybody off the top of their head know the conversion factor for day to seconds? Somebody might, but if you do, don't say anything because then you ruin the exercise. Okay? So we don't know off the top of our head, for example, how many days or how many seconds there are per day, right? I mean, maybe one of you does, but you do know how many seconds there are per minute, right? And you do know how many minutes there are per hour, right? And you do know how many hours there are per day, right? All right, so let's do that with our grid. Does that make sense? So what we're going to do is we're going to build, in this case, what would be a 4 by 2, putting in each of those conversion factors and seeing if our units cancel at the end. Okay, so go ahead and give a stab at that. I'll give you like 2 minutes, and then we'll come back and we'll do it together. All right, who's got it? Willem? What do you have for your answer?
I'm not sure if we're going to 86,400.
86,400? That sounds about right. Does everybody have that? Who does anybody have anything different? All right, so let's walk through this together, okay? So we set it up like this. Hopefully you guys set it up like this. We have 1 day and then 24 hours per day, 60 minutes per hour, 60 seconds per minute. And then what do we do? What did you do next, Willem? So you set it up like this, right? Ish? And then what'd you do?
You just multiply over based on the ratio. So if there's 24 hours in a day, you have the 24. And you know you have 24 hours, and since each hour is 60 minutes, you multiply the 24 by 60.
Perfect.
And since take that number, and since there's that many minutes, you just take the ratio for minutes into 60 seconds.
Perfect. So what it's going to end up looking like is this, right? What do? We cancel the days cancel, the hours cancel, the minutes cancel, the second stays there, so that means we have 60 seconds as a unit, or we have seconds as a unit, and then we go 1 times 24 times 60 times 60 equals 60 seconds. Okay, so this was a little more complicated than the first example we looked at. What's going to happen is as you start getting, right, maybe you'll be looking at a flow rate, and in the case we were talking about earlier, right, we're looking at a mass flow rate, and now we also need to have the density, but the density is not in the right unit, so now we need to convert the density into something, and all of a sudden you have, but the point is you can get this wide thing going with multiple conversion. It's all still one problem and it's equivalent. And then at the end, if you don't get the units you wanted to, you can go back and look at each individual column and make sure that you have them flipped correctly, right? Because it doesn't matter, in theory, whether we put something on the top or the bottom as long as that ratio is accurate, correct? But in the end, if we don't get that in the right order, in this case, if I had screwed up and I had said, all right, I know there's 60 minutes per hour, but I put the 60 on the bottom and the 1 on the top, what would have happened to our number? It would have been wrong, but what also would have happened to our units? They would have been wrong. So we can go back and we can identify the box and just flip that, right? Because you will very easily make conversion error factors if you don't track your units very carefully. And as you guys, I'm sure, know very much from physics or chemistry, if you get, right, that's actually one of the cheats that you can learn when you guys are taking like your AP tests, or you guys are IB, right? You guys are taking your IB tests if it's multiple choice. Sometimes they'll have answers on there that the units don't match up, and you're like, I know this needs to be a velocity, but that's an acceleration. It ain't B, right? It's the same concept that you guys already use on some of those tests, right? Just use it and you know, all right, this doesn't work. Next. All right, so now number 7, this one's going to be a little more complicated. So this is page 7 in your handbook. A faucet is leaking at a rate of 1 drip per second. Each drip is, on average, 1 centimeter cubed in size. How many gallons are wasted over the course of a week? All right, so real quick. So Andrew, talk me through this one. How many things do I have going on here?
You have a drip, which is 1 centimeter cubed in size. So you've got 1 centimeter cubed per second.
Okay.
Right? And then you have to convert the centimeters into gallons, and you have to convert the seconds into a week.
Perfect. So we've got 3 different conversions going on at the same time. All right. So now let's set up our grid. Make sure we get all of our info in there, and then start adding the conversions as we go, and let's see what we get. So I'll give you guys a couple of minutes, and let's see if we can do it. All right. Let's go ahead and move on just for the interest, or not move on, but let's go ahead and get ready just for the interest of time. All right. So who's got an answer for me? Nobody wants to, somebody's got an answer except people looking up. Nobody wants to volunteer. You got one? Or give it a shot? All right, what do you have?
I have 604,800.
604,800 centimeters. I see nods. See, you did have one. All right. Fair enough. All right, so talk me through it. How'd you do it?
So I had the table as 1 week, 7 days per week, 24 hours per day, 60 minutes per hour, 60 seconds per minute.
Okay, that block there. Go ahead.
And 1 centimeter squared per second.
Okay.
Which left us with the unit of centimeters cubed, I think that is. And then I multiplied them all out.
Okay. So you just multiplied them all out. So what I got was I got this here. So I went from drip to second to volume per drip, and then correct your time conversion there to week. And then I went from centimeters to milliliters, milliliters to liters, and then liters to gallon. And then that left me with 60 times 60 times 24 times 7 gallons divided by 1,000 times 7, or 3.785. That gives me 159.8 gallons per week, right? Because we wanted the answer in gallons, right? So very simply here, what we did was we converted our drip into a volume, our rate into the time that we needed, and then we converted our volume into the volume that we needed it. Yes, sir?
Do we know the conversion from liters to gallons?
So those conversions are in the back of your book, luckily. But yes, that's another one that you'll learn over time. Why is liters to gallons a very common one that you see? Does anybody drink milk? The top of the milk jug, it says 3.785. Okay, so actually let's go ahead and look at that. So may I, there's a book over here. So good learning. If we go to the back, let's go ahead and 234. That may not be, here we go, yeah. So 232 is an appendix which has conversion factors for volume. So you can use that. So if I were looking, for example, the one that I needed, if I needed to go from centimeter into gallons, where would I find that? So I see gallon US fluid there in about the middle of the page. And I can convert it to inches squared. And then I can also put it into, or not squared, sorry, inches cubed. And I can put it into meters cubed. And then it also has, see there on that very far right side, other usefuls, 3.78541 liters. Do you guys all see where I'm at here in the middle of the page? So we are right here. Conversion factors for volume units on page 232. So if I say if I have 1 gallon is equal to that many inches cubed, is equal to that many meters cubed, and it's also equal to 3.78541 liters, 128 ounces, 8 pints, or 4 quarts. Have you guys ever used conversion tables before? It's really no different than looking up anything in just a data table, right? Just gives you what you need. Good learning. Excellent question, Will. But yes, by the end of class, you're expected to have that memorized. No, that's why we put them in there, right? That's one of the great things about engineering across the board. Unless you will get that professor, it's going to happen. But there's this magic thing in engineering where they don't hide the book, right? A lot of your engineering tests will actually be open book because it's not about, right? We've talked about this in engineering. It's not about learning how to do. It's about learning how to solve the problem. It's not about memorizing the problem, right? If it's a problem you can memorize, there's no reason to pay you to do it, right? Just give you a book, have you go memorize it. It's not a spelling test, right? It's a problem solving, right? So they have no problem with you having your book. They want you to reference it. They want you to have the information at hand. It's not about the problem itself. It's about learning how to solve the problem, right? So your book is absolutely at your disposal. All right. So this brings us to another one, and this one is kind of a problem. Why is temperature kind of a problem from a conversion standpoint? What do you think, Michael? Why is temperature kind of a pain in our butt?
Is it because doesn't have like a linear.
Very good. Yeah, so it doesn't have a direct conversion factor, right? Because you guys probably off the top of your head at least are familiar with how to convert from Fahrenheit to Celsius. What is that equation? There's like a 9/5 in there, or a 5/9, depending on which direction you go. There's a plus, what's the magic number? 32, right? Or minus 32, right? Depending on which direction we're going. Right, so the problem, let's just say it, with temperature, is that you need both what we call scaling, which is that's your conversion factor, but you also need translation. You need to shift it up or down, right? Because remind me, what's freezing in Celsius? 0. And what's freezing in Fahrenheit? Well, that doesn't make any sense. So what we need to do is we need to subtract the 32 to get it down to that value, and then there's still a translational factor, right? So this table here, again, I expect you to have it memorized within the next 30 to 40 seconds, right? But we have 4 different temperature. So you guys are very familiar, obviously, with Celsius and Fahrenheit. You can't grow up in this country and not be familiar with both. It's just the way it is. Most of you guys, or through your science classes, are familiar with Kelvin, right? What's Kelvin? 273. And why is it 273? It's actually 273.15, right? Yes. So what is 0 degrees Kelvin? Does anybody know? What is it? Absolute zero. And what does absolute zero means? It's when everything stops, right? Everything, it doesn't even die. It's just like everything stops, right? That's the idea of absolute zero, right? You guys are both correct. So you guys are familiar with Kelvin. Rankine, so this is an absolute temperature scale. That's what that means. Rankine, the little degree R, is the Fahrenheit version of Kelvin. It's just the Fahrenheit version of absolute zero. Okay, so it adds another crinkle in your plan. So you just need to be able to convert between these guys. And again, I don't expect you to have you memorized, but there is a table in the back of your book. Some of these equations, honestly, like I still forget whether it's 9/5 or 5/9, right? You're gonna have to look it up. You're gonna have to OK Google it or Alexa it or whatever, right? It's fine, it's in the back. That's why we don't hide the book. Maybe you guys are familiar with this. So SI unit prefixes, you guys already nailed this because I asked what's a kilo and you guys said what? 1,000, right? What's a mega? A mega, not so, or omega. What's a mega? What's that? Million? Is it? I don't know, let's look. It's 10 to the 6th, it's a million. Nicely done. All right, and then we of course have the other side of it. So we have the positive side of the scale, which is what we're talking about. Kilo is 10 to the 3rd, which means it's times how many tens? Times 3 zeros at the end, right? 6 is how many zeros at the end? It's 1,000,000, 6 zeros. What's 9? Everybody knows that. That's what I make per year is billions of dollars, right? So 9 zeros at the end. Okay, and then from there we go on to what you guys are all going to make, which is yadas, which is 10 to the 4th, all right? But then we go the other side. Now we're all quite familiar with these. Decimeter, actually deci we don't hear very often, right? But centimeter, we all know that that's how many? How many centimeters per meter? 100, and that's kind of frustrating because don't we like to work in groups of 3s? I like to work in groups of 3s. Okay, millimeters are actually they're easier to deal with, right? Groups of 3, so there's 1,000 milli. We then go to micro, which is your opposite of your million, meaning there's a million in the 1. Then we get to nano, which is the current buzzword in the world. Nano is 10 to the -9th. And then we can keep going beyond there, but you're not really going to have to worry about stuff below nano very often. Okay? Does anybody know what an angstrom is, by the way? An angstrom is the unit we use to measure like a lot of atoms size. It's actually to the 10th, right? So they're -10. Okay? So we all have this down, right? Good? All right, yeah, not news to you guys. The reason I bring this up is because it brings us to something that you guys are going to hear a lot, especially who are my environmental engineers? You wanted to be an environmental, right? Yeah, and you're going to be environmental. So you guys are going to hear the joke in environmental engineering, which is that dilution is the solution, right? If we have a poison in the lake, we just keep putting water in the lake until we can't detect it anymore, right? Doesn't mean there's not still some trace amount of poison there, but we need to get rid of it. Okay, so parts per notation is something you guys are going to see a lot. What I mean by that is, you guys have heard this, parts per million, parts per billion, parts per trillion. A good example of this that you guys have probably all dealt with is a swimming pool, right? The concentration that they keep chlorine at in a swimming pool, what do you guys think it is? Is it parts per million, parts per trillion, parts per billion? What do we think? I don't know. Fair enough. All right, it's usually parts per million, right? So the most common, actually, parts per measure is something we use every day instead of being all fancy about it, right? Who knows, who went to a sale? Did anybody buy clothes on sale within the last couple weeks? Christmas a couple weeks ago, I guess. Maybe bought something off sale. When we put something on sale, how much off is it? 20%, 30%, right? A percent is just a parts per notation. It literally is percent, which is how much? Per 100, right? So if I am 20% off, I'm taking off 20 per 100, which means I save 20 cents on every dollar, right? So that's just a parts per that we use, okay? The other common ones are ppb, ppm, ppb, and ppt. Do note that parts per thousand is not a used nomenclature. Why would that be? Because what would the note for parts per thousand be? PPT, but then parts per trillion is also PPT, right? So again, we're sticking, that's why I said I like rules of three. And this is not a this class thing, it's just the way it is. Parts per thousand is not a thing because it's confusing with PPT, which is parts per trillion, right? Did you have a question? Okay, cool. So yeah, a lot of the time when we are talking about like dilution of pollutants or something in a lake, we'll be on the parts per billion or parts per trillion type of scale. All right, so parts per is pretty simple. Suppose we have 1 milliliter of contaminant in 1,000 liters. Wait, remind me, what is the exponent on a milliliter? 10 to the third? 10 to the negative third, right? So I have 10 to the negative third in 1,000 liters. So that's 1,000 liters. Liter is your basic unit, right? And 1,000 is how many? 10 to the 3, right? So what we have up here, as we just talked about, we have 1 milliliter in 1,000 liters. We have negative 3 divided by 3. What do we do with exponents in that case? Subtract them, right? So we have negative 3 minus what? Minus 3, which brings us to what? Negative 6. Are you guys sure? Okay, yes. All right, so what we get is negative 6, which is 1 part per how much? Million, right? Because million is how much? To the 6th. So we have 1 part per million. Okay, very simple. So again, if we are making sure that our chlorine in our swimming pool is at the correct, we would say, all right, I have a Olympic-sized swim. Does anybody know off the top of their head how many gallons are in an Olympic-sized swimming pool? I have no idea, right? But it's a lot. Okay, so I have this Olympic-sized swimming pool, and I need to keep it at so many parts per million. So what are we going to do? We're going to add 5 pounds of chlorine or something like that, right? And then once it's all diluted, we're all super happy. That's really all it just boils down to, okay? All right, where's my chemistry? Actually, let's do it this way. Where are my guys that haven't taken chemistry? All right, a couple of you guys. All right, so of those guys who have their hands up, do you guys know what a mole is? A little brown creature that lives in the ground? Fair enough. All right, so a mole, well, how about, where's somebody who feels super good and confident at chemistry? Nobody? Kate, you want to take a shot at it? You want to explain to people what a mole is? What's that? So if I have 6.02 times 10 to the 23rd amount of something.
Number of atoms in a mole.
Yep. Right, or well, 6.02 times 10 to the 23rd, right? I'm getting that right?
Yep.
Right? Is the number of things in any number of those things defines a mole. And ideally, what that means, not ideally, in practice, what that means is if I have a mole of molecules, I have that many molecules. So if I have a mole of oxygen, I have that many oxygen atoms, right? Then we can use that to go to our handy dandy periodic table, and we can look at oxygen, and we know what the weight of a single oxygen molecule is that we define in this is what? Molecular mass. And then we can use that to define what the mass would be of a mole of oxygen. What's interesting about it in this case is a mole is not a defined mass. It's a number of, so a mole of hydrogen and a mole of oxygen, would they weigh the same? No, because it's the same number and they would thus weigh differently. And then even interestingly, if I had 1 mole of water, would that mole of water weigh the same as 1 mole of hydrogen? No. Would it weigh the same as 1 mole of oxygen? No. Would it weigh the same as 2 moles of hydrogen and 1 mole of oxygen? If I put them on a scale, would they weigh the same? It should, right? Because what's the formula for water? H2O, so 2 hydrogens for 1 oxygen. So if I have 2 moles of hydrogen and 1 mole of oxygen all in a bucket, and then I have 1 mole of water all in a bucket, they should weigh the same amount, right? Now, would those take up the same space? Probably not, right? Depends how close to absolute zero we get, but probably not, right? All right, so the point is, in defining that, or in going through that, a mass fraction is mass of A divided by the total mass in that mixture, right? So let's say in the case that we talked about water, it is hydrogen and oxygen, right? What would be the mass? Anybody remember what the molecular mass of hydrogen is? It's a super easy one. What is it? 1. What is the molecular mass of oxygen? Everybody remember that? 16, right? And then there's like a 0.004 or something on there, right? But we call it 1 and 16 because we're engineers and it's close to darn enough, right? So if I wanted to know what the mass of my hydrogen was in this water mixture, what would it be, roughly? It'd be 2 divided by what? 18, right? 16 plus 1 plus 1, right? However, so I just gave you guys a bad example because it's going to work out the same, right? Because 1 and 1, all right? But point is, if I have, let's say I have 50 grams, let's do it this way. I have 50 grams of hydrogen and I have 50 grams of oxygen and I mix them together. What is my mass percent of hydrogen in that mixture? What is it? It's 50 over 100. So my mass percent is, or my mass fraction, it's going to be 50% or 0.5, right? But now let's convert it to moles, okay? What does 1 mole of hydrogen weigh? 1, right? What does 1 mole of oxygen weigh? 16, right? So then I have 2 moles, so now I would have 2 over 16. Is that still 50% mass? No, right? So what we're starting to see is that there's a difference between mass fraction and mole fraction, right? Mass is looking at directly the mass. Moles are not mass. It's something very different, okay? So the takeaway here is the mass fraction is just mass divided by the total mass. Moles of A is the moles divided by the total moles in the mixture. Do we expect our mass fraction and our mole fractions to match? The exercise we just went through is no, right? So we have to treat them very differently. Okay, and everybody understands what a mixture is, right? Okay, so it's just combined when we combine 2 or more things in a way that it's important no chemical reaction occurs. And that's why I realized halfway through that little thing that using oxygen and water was not the greatest example. Okay? All right, so the point is, takeaway, mass and mole fractions, they're not equivalent. So how do we figure out a problem where we have masses and then we have mole fractions? How would we go about doing that, River? What do you think, Aditi? How would we go about figuring out our problem where I need to go from mass fraction to mole fraction?
First, like, figuring out the total, like, starting with the mass,
Mhm.
figuring out the total mass. And figuring out the different components of the mixture.
Mm-hmm. You're very, very, very close. The problem is we don't know how much we have, right? We just know that what we have is 50%. So where would you start? What we have is 50% by mass A. Where would we start? And you already talked me through it. I think you've got it. What we're going to do is we're going to start with what we call a basis of calculation. Okay, basis of calculation is just saying, let's assume that I have 100 grams. Because it doesn't, you're just looking at a percentage. It doesn't matter if that 100 grams is accurate or not. You could say I have 1,000,000 pounds. It doesn't matter. But you're going to find what percentage of that 1,000,000 pounds. And then now that you have a workable number, you convert it to moles. And then you back it out, and then you can get your mole fraction. Okay? So let's do page 8, sample problem. A cleaning solution is 50% by mass water and 50% by mass bleach. Bleach has the chemical formula NaClO. What is the molar composition of the cleaning solution? I'll give you guys 2 minutes, and then we'll work through it together. Real quick, what's the molecular mass of sodium? 23, right? Is that true? Where's sodium? Over here. Is 22.98, 23. Does anybody know off the top of their head molecular mass of chlorine? 35. Yep, very good. Yep. And then what did we say O was? Remind me? 16. Perfect. And what are the units on that? Grams per mole. Very good. Or kilograms per kilomole. All right, so let's go ahead and start walking through this, okay? So what we're going to do, and there should be a table in there that you guys are filling out, all right? So what we're going to do here is we're going to set a basis of 100 grams. So this means that we're going to assume we have how much water? If I have 100 grams as my basis and it's 50% water, how much mass water do I have? 50 grams. And then how much does that leave left for my bleach? Well, why can't it be 60? Why can't I have 50 and 60? Because it's greater than 100%, right? Yes, perfect. Very good. So if we plug that into our table, what we get is our first column's all filled out. 50 grams, total's 100 grams. We're at 100%. We've accounted for all of our mass. We're happy. Okay? Go down the hall, get a coffee or whatever, and then we'll come back and start plugging out. Okay? That leaves us with our mass fractions, which we know, which are 50, which adds up to what? 1. We've accounted for everything. We're good to go. Table, we put in our molecular weights. I actually put in the actual one, so water there is 18.02. The bleach is roughly 74.5. And then we do our mass to mole conversion. How many moles do we end up with? We end up with 50 divided by 18.02 equals 2.77 moles water. And then we have 50 divided by 74.44. Again, this is just our unit conversion. Equals 0.67 moles of bleach. And what's cool about this, right? What is this? Even though we had some people who didn't know how to do a conversion between mass and moles, as long as we knew what the units were, we were able to figure it out just by canceling units. And that's pretty cool. All right? So that leaves us with 0.67 moles of bleach. Now, what is our mole fraction? We take 2.77 divided by 3.44, which is our total, and that equals 0.81. And then 0.67 divided by 3.44 equals 0.19. And then what does that add up to? 1. Crazy how that works. But, so we started off with a mass fraction of 50%, but what did we end up with a mole fraction of on water? Way higher, and we ended up with way less of a mole fraction on bleach. And why is that? What's that? There's more moles of water because 1 mole of bleach weighs way more, right? All right, do we have any questions on that? All right, so what we're going to be talking about today, right, we're going to continue the rocket problem that we talked about last week. But functionally, why I like to do Excel after this is, could you imagine now, put yourself in the shoes of a chemical engineer who's trying to do a mass fraction or mole fraction assay, is what they call it, on crude oil, right? There's millions of components of crude oil. Do you guys really want to sit and do this by hand? The answer is absolutely the heck not. Instead, what you might do is put it into an Excel program where it calculates it all for you. Or I should say a spreadsheet. Right, I confuse it because I use Excel, right? But a spreadsheet is what I'm talking about, okay? So that might help you, and you could even write an Excel or a spreadsheet program that would help you plug in those things and put it where you need to go and solve it for you, right? So that way you don't have to go through and spend 2 days doing your calculations. Instead, you have it right there for you. Okay, so that's why I like to talk about that tonight. So that is the end of tonight's lecture. Looks like we are right on track. Do we have any questions on this before we go forward? Okay, perfect. So what I want to do is please take a 5-minute break, go get a glass of water, pull out your laptops and get them started, or Chromebooks or whatever you brought. If you didn't bring one, find a buddy, be best buds, and make sure you pair up, and then we'll come back and get started. All right? See you in 5 minutes. Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD. While the textbook is not essential to successfully follow all class videos, It is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.